Okay, this is video 10.1, the fourth video about momentum. And you may remember from chapter 9 that we defined the quantity momentum, and we also looked at center of mass, but momentum is P equals mv. And there was a similar quantity called energy that we're going to see is sort of related. And we said that you increase the energy of a system by doing work on it. So what we want to know is what quantity changes the momentum of a system. So the question is, how do we change the momentum? And that means changing the velocity. And the short answer is apply a force. And we know that Newton's second law can be written F is the time derivative of momentum, and that means if we multiply by dt and integrate, we can see that the change in the momentum of the system is equal to the integral of the force with respect to time. And this quantity, F dot dt integrated, is called impulse, usually written as J, or if the force is constant, F delta t. Notice that J, the impulse, is a vector, and that J is equal to delta p. So the impulse on a system results in a change in its momentum. Work has a similar form. Work, remember, was F dot dx, or F dot delta x, but there's some differences. In impulse, we have a vector F times a scalar t, and you end up with a vector J. With work, you have a vector F dot product with another vector x, and you get a scalar. So impulse has direction, work does not. Impulse equals the change in momentum, and work equals the change in energy. And these two ideas of energy and momentum are tremendously important things in physics. And you'll find if you go beyond this level of physics that you talk about work, energy, momentum, impulse much more than you talk about forces. And there's a whole series of problems, like for instance problem 8 in your book, that deal with a series of collisions. I believe problem 8 involves Superman getting hit with machine gun bullets. So I don't know the numbers from that problem, but there's Superman, and there's bullets coming in, and they bounce off of him. Everyone knows that. And if we say that the bullets each have a mass of, say, 15 grams, and let's say they have a velocity, or an initial velocity, of 700 meters per second, and they bounce off going 700 meters per second in the other direction. So the question, and then the rate of fire, so the number of bullets, let's say it's 600 bullets per minute hit him. And so the question is, what is the average force exerted on Superman? Because of Newton's third law, that's the same thing as asking, what is the average force that Superman exerts on the bullets? And that force is equal to the change in momentum over the change in time. Since we're doing averages, we don't need to actually use a derivative. We can just do the delta p over delta t. And that means the total mass of bullets that hit Superman in a time delta t times the change in velocity of each bullet. And so if delta t is 1 minute, then the total mass that hits Superman is 600 times 15 grams, which is 0.015 kilograms divided by 60 seconds. And the total change in the velocity is 1,400 meters per second because the bullets change directions. And that means that the force is going to be about 210 newtons is the average force exerted on Superman. So that's a particular kind of problem that frequently throws people off. There's an entire XKCD what if that deals with this, basically asking, could you use a machine gun to lift yourself into space? The answer is sort of, but that's how you work that sort of problem. Now, for our last slide, we'll look at another example. This is problem 10 from your textbook. You've got a softball. It has an initial velocity, 12 meters per second, 35 degrees below the horizontal, and it's hit by the bat, and its final velocity is 10 meters per second straight up. We know that the ball is in contact with the bat for 2 milliseconds, and so the question is, what is the average force on the ball? Once again, we'll say force equals delta P over delta T being 2 milliseconds. For delta P, that's m delta V over delta T. Now we need to find the delta V of the ball. So delta V as a vector is equal to vector VF minus vector VI. VF is 10 j hat. VI, if you break it up into components, ends up being 9.8 I hat minus 6.9 j hat. So we get negative 9.8 I hat plus 16.9 j hat is the change in velocity. Now the magnitude of the change in velocity, if we use the Pythagorean theorem, works out to 19.5 meters per second. And that's what we're interested in because we're looking for the magnitude of the force. And so plugging in numbers, we find that the average force exerted on the ball is 2,930 newtons, which is rather large. You think, well, a softball isn't that big and its velocity isn't changing that much, but it's changing in a very small amount of time, therefore the large force. What I'm going to check tomorrow are questions 1 and 3 from chapter 10.